Je vous souhaite la bienvenue à la session télécommunications. Géomatique 2011 est initiée et organisée par l'ACSG Section Montréal. Premièrement, nous tenons à remercier notre partenaire principal, le gouvernement du Québec. Nous vous rappelons qu'il est important d'éteindre vos téléphones cellulaires. Les présentations de cette session seront d'une durée de 20 minutes, incluant la période des questions. Dans le premier volet, nous allons avoir deux conférences, une par M. Maïsen Argani et une par M. Martin Chevrier. Maïsen. M. Argani est candidat au doctorat en système d'information géographique au département de foresterie, géographie et de géomatique de l'Université Laval. Le titre de sa présentation est « GIS-Based Wireless Sensor Network Deployment and Optimization ». M. Argani va faire sa présentation en anglais.
Good afternoon, everyone. I am Maïsen Argani, PhD candidate in geomatics in Center for Research in Geomatics in Laval University. My presentation is about a GIS-based wireless sensor network deployment and optimization. First of all, my outline of presentation is going in introduction. Actually, I'll introduce the sensors and the sensor network, and after that I'll talk about problems and challenges in sensor networks. Then I'll try to define our project, and I'll try to tell you about our proposed method to solve the problems, and then I'll introduce some initial implementation of our project and actually of our project framework, and finally my conclusion. So what is the sensors and what is the sensor network? The sensors are some small and smart devices which can sense many things in the environment. For example, they can sense the air pollution, they can sense sound, they can sense fire. And when we put together this sensor, we can have the sensor network which can deploy in the environment, in inaccessible environment, and we can remotely sense something that we cannot have some information from them when because we cannot have access to them. In terms of application, I've divided the application of sensor network into three main categories. First of all is remote monitoring, and then sustainability and industrial measurements. In remote monitoring, there are many interests to have some information about the air and about the climate, and as well as there is many interest to have some information about the soil, about the water, and actually you know that there is many possibilities to have some information remotely from some indoor spaces. For example, maybe you want to have some information from your home, from your business, from your factory, from your industries, or something else. In terms of sustainability, I can say that power quality and consumption monitoring is very important in sensor networks, and we have many applications in it. Solar monitoring and wind monitoring are other two different applications of sensor networks. In terms of industrial measurement, we can do some monitoring on health in important buildings, for example, in important structural, in important structures, for example, in a dam. We can control the process in factories by sensor networks, and we can monitor the machine health in the factories by using the sensor network. Actually, we can divide the sensor types in two categories, passive and active. And both passive and active sensors have two different parts. non-scanning and scanning, and both of them, non-scanning and scanning, have two other parts, non-imaging and imaging. For example, a gravimeter is a sensor which is non-scanning, non-imaging, passive sensor, and so on. As you can see in this slide, there are many sensors available in the market. For example, gravimeter, sensor for sensing fire, sensor for security. If you take a look around, we can find many sensors in our life. For example, you can see many sensors in this building, in your apartment, and everywhere. The sensor technology, actual sensors are getting cheaper and smaller. For example, if you see this image, previously sensors are very big and are very huge, but right now we have some sensors, for example, like this, as big as a bin. So sensors right now are very small and actually are very cheap. In terms of problems and the research challenge, I've divided our research challenge into three main categories: communication, processing, and spatial coverage. In terms of communication, I can say that we should know the sensor topology, because we should know how sensors can send and receive information between each other and between the main part, for example. For data processing, sensors, because sensors gather information from different sources of data, they have actually they should process many different kinds of data. So we should manage these different kinds of data, and we should do the data fusion in the sensor networks. After that, sensor programming and interface is very important, and because the sensors deal with very huge amount of data, we should make a good solution to manipulate this huge amount of data. And if we want to put these data on the web, we should find some ways to put these kinds of data on the web. But our more important part of our project is coverage in the sensor networks. In my project, we try to find best coverage and best position for the sensors in two different approaches: in global approach and in local approach. In global approach, we try to find the best position for the sensors globally, but in local approach, we try to find local position for sensors for so now I can define our project. First of all, I want to speak about our problems in the project. As I said, we focused on the coverage problem in the sensor network. So we try to place minimum number of sensors in the environment to have the best coverage in the environment. Based on this general problem, we have three specific problems. First of all, we want to consider the environmental information in sensor network placement, and after that, we want to consider the dynamics in both sensor networks and the environment, and we try to do the data accuracy assessments. Regarding to the problems, we have these objectives. Our general objectives is that we try to find the best sensor location to have the best coverage, and actually we have three specific objectives. First of all, we try to use GIS to consider the environmental information in our project, and we try to consider some geometric approach to consider the dynamic in environment, and we try to perform an accuracy assessment. We have a hypothesis in our project. Our hypothesis is that if we integrate the environmental information in both aspects of geometric data structure and optimization algorithm, we got better optimization, we got better optimum position for the sensor network. And to prove this hypothesis, in the next slides I will show you some implementation of this hypothesis. Those problems and objectives lead us to define a project in GEOID. Its name is GEOID Section 4, number 70, Integrating Developmental Genetic Programming and Train Analysis Techniques in GIS-based Sensor Placement System. Actually, we have three main scientific groups in this project. One group is in geometric, another group is in optimization, and another group is sensor modeling. For the geomatics, we have a team in University of Laval, and for electrical and computer engineering, we have two teams in University of Calgary and in Laval University. Actually, the optimization group is in Laval University, and the sensor modeling group is in University of Calgary. Our project is very interesting actually for industries. We have some partners in industry, and we have three collaborators: Defense R&D Canada, Valcartier, MDA System, and INO. Actually, as a PhD student in geomatics, I tried to introduce our project in aspect of geomatics. So I divided my PhD project into 4 phases, phase 1 to phase 4. In the first phase, I've collected some information about, actually some data sets to execute our project. We have 3 different kinds of data sets. One data set from an urban area, and actually 2 data sets from urban area, and 1 data set from a natural area. One from Quebec City, another is from Laval University, and another one is from Montmorency Forest. In the next phase, in phase 2 of my project, I try to define a conceptual framework, and I'll try to use the different environmental elements in different layers in a GIS system. So I'll define a GIS, and I'll consider the environmental elements in different layers, for example, the buildings, the roads, and so on. And after that, we try to define some rules in our knowledge database to manipulate our data set. In the next phase, in phase 3 of our project, we try to make a data structure for considering the dynamics in the network and in the environment. For example, if we and for doing this, actually, we consider Voronoi diagram because it's very useful to such kinds of project. For example, if you consider that we divided our environment by using the Voronoi diagram based on the position of the sensors, consider that these points are the position of the initial are the initial positions of the sensors. We can consider that the sensing field of each sensor is a circle around each sensor, and by dividing the environment with Voronoi diagram, we can find some places that we don't have coverage on them. For example, in this picture you can see the gray area which doesn't have coverage on them. So what is the solution? The solution is we have actually 2 different solutions. For example, we can insert some new points, new sensors, or we can move the existing sensor. How we can insert the actually there are 2 different there are many approaches to know that how we can insert new sensors and how we can move the existing sensors, and actually I don't want to go deep to define these algorithms, but for example, for moving the sensors, we can consider that each sensor can move toward the farthest Voronoi vertex to cover the whole areas. And at the final phase of my project, we try to do data quality and uncertainty and assessment in terms of positional accuracy, attribute, temporal accuracy, and etc. This picture shows the different phases of my project, actually. First of all, we try to insert the reality in a GIS database and make different layers for different phenomena. And we try to make a knowledge database which defines some facts and rules. And after that, we try to make a simulation engine to put new sensors and move the existing sensors. This is the initial implementation of our proposed framework. Actually, to prove our hypothesis, if you could remember, I said that our hypothesis is that we want to make better deployment by inserting the environmental information. So I considered two different kinds of data sets, one from urban area and another from a natural area, a small part of Quebec City and a small part of Montmorency Forest. And we considered that our study area were covered by 10 sensors with sensing range of 50 meters. So, and we considered that each sensor could rotate between -90 and 90 degree vertically and between 0 and 360 degree horizontally. In these two pictures, you can see the initial position of our sensors, and you can see the Voronoi diagram, and you can see the sensing range of each sensor. So we can find that in this area, for natural area, for example, and in this area, in our urban area, we don't have any coverage. Actually, in these two pictures, you can see the covered region of the sensing field of each sensor node in their initial deployment. If you consider, we have viewshed between the sensors and between the sensors and elements, and then we overlaid these viewsheds and the sensing field of each sensor, we can find that the green area have visibility, and the pink area doesn't have any visibility. This is the visible and invisible area after doing the optimization. In our optimization, we consider that each sensor can move toward the farthest Voronoi vertex, and it will stop when it reaches the higher elevation of its initial elevation. So, in this table, we can compare the different results on urban area and natural area. For example, we've had 22% of visibility, but after the optimization, we have 34% visibility. And for natural area, we've had 67% visibility, and after doing optimization, we have 71% for visibility. So this initial implementation shows that our hypothesis was true. For conclusion, I can say that the previous methods in literatures almost oversimplify the coverage problem, and they do not consider the characteristics of the environment. And we find that Voronoi diagram and Delaunay triangulation are very good solutions to manipulate the coverage sensor network. And actually, the Voronoi diagram and Delaunay triangulation have their problem when they used in more complex areas, for example, in areas with some obstacles. So our near approach was proposed, which consider spatial information, and to evaluate our proposed approach, two different data sets were investigated, and some promising results were obtained. Thank you for your attention.
Merci beaucoup, M. Argani. On a le temps pour une ou deux questions. C'est des questions? C'est beau. Merci beaucoup. Notre prochaine conférence sera donnée par M. Martin Chevrier.